Okay, the first problem talks about number one, what is the pH of a buffer that has a concentration of acetic acid as 0.15 molar and sodium acetate as 0.25 molar, and they give you the Ka. So all they're doing is asking what the pH of a buffer is. So I would start with the buffer equation. The concentration of hydrogen ions equals the Ka times the acid over the base. So in some problems there's neutralization where you add something strong. This is not one of those problems. All this is saying that you have a weak acid, HC2H3O2, and it's 0.15 molar, and you add some sodium acetate to it, and that is 0.25 molar. And really what it is you have an equilibrium of a mixture of the acetic acid molecule and the acetate ion. And this is what you normally have in a weak acid, but you've upped the concentration of the conjugate base ion that's normally there by adding a salt that contains that ion. And so you're shifting equilibrium. So really this is just the Ka expression rearranged to help us solve for pH and focusing on the acid to base ratio that we see in the buffer. So all we're going to do is plug in our Ka value, which is 1.8 times 10 to the negative fifth. And then when you go to use this acid to base ratio, you can use molarity, you can use moles, you can use millimoles, but you can't use a combination of each. So because they give you the molarity, the concentration according to each thing, you didn't need to know the volume. You just go ahead and put the molarity in. The acid is the acetic acid, so we're going to put 0.15 molar, and the acetate is 0.25 molar. And you have what you need, and you solve for the H concentration. And that gives you 1.08 times 10 to the negative fifth molarity. And then we know if we want the pH, we negative log the hydrogen concentration. So that would give us a pH of 4.97. So this is just strictly a buffer solution that was made, and you were able to get the pH by looking at the Ka expression and solving for the hydrogen concentration. All right, so we're going to go ahead and do number two. So number two says you mix some ammonia with ammonium chloride. So it's the same kind of problem, except in this one you have ammonia, which is a weak base, and you have ammonium chloride, which is a salt, but it contains the conjugate base ion, or conjugate acid ion. So it's a mixture of weak base and conjugate acid. You haven't done any neutralization. You haven't added any strong acid or strong base. So we're just looking at that buffer equation. The only issue now is they're giving you volume of one concentration, and you're mixing it with volume of a different concentration. So the volumes combine, and when the volumes combine, the concentrations change. So it's like doing a dilution, where you have to consider the new concentration, or you could look at the relative amount of moles or millimoles, which is probably easier in this case. So I'm going to go ahead and write ammonia and the ammonium, but they're not reacting with each other, so I'm not going to write a reaction. And underneath the ammonia, I'm going to say that that was 0.1 molar, and there was 40 milliliters of it. So if I multiply molarity by milliliters, you get millimoles. So you have 4 millimoles of ammonia in that 40 milliliters. So when you combine it with the ammonium chloride, that doesn't change. And then the same for the ammonium, it's 0.2 molar, and there's 20 milliliters of that. So you have 4 millimoles of the ammonium. So it's a buffer, it's a mixture of both the weak base and the conjugate acid. So we can go right to the buffer equation. Hydrogen concentration equals Ka times acid over base. Now something that's different here is you have a weak base with a conjugate acid. You could take this whole equation and rearrange it, so it gives you like the hydroxide concentration equals the Kb over base over acid, but I think that gets confusing, so I would just stick with this equation. It's just we're going to have to fix the K that they give us to get the Ka. So again, I'm going to just use the millimoles because in this ratio you can use millimoles, moles, or molarity. And if I tried to find a molarity, what I would end up doing is dividing both of these by 60 anyways, because they are in the new same total volume, so that's not going to matter. So we're going to solve for the hydrogen concentration. And again, don't get confused, but we need Ka. We're going to stick with this one equation for all the buffers. So we need Ka, so that's the Ka of the acid, which is the ammonium ion. And they give us the Kb of the ammonia, which is 1.8 times 10 to the negative fifth. So we should know that we can get the Ka by taking 10 to the negative 14th divided by that, because the Ka times the Kb for any conjugate pair is always 1 times 10 to the negative 14th. So I'm just going to go ahead and put 1 times 10 to the negative 14th here and divide by the 1.8 times 10 to the negative fifth, which gives me my Ka for ammonium. And then again, just be careful, we're doing acid over base, and the ammonium is the acid, which is 4 millimoles, and the base is the ammonia, which is 4 millimoles. So you have equal acid to base amount. So if we were doing a titration, you should understand that this happens at the half equivalence point. So the hydrogen concentration simplifies to the Ka, where we see pH equals pKa. But again, all this is a buffer. We haven't done any neutralization to form the buffer. We just mixed the weak base with its acid salt. So this ends up being hydrogen concentration is equal to 5.56 times 10 to the negative 10th. And so to get the pH, we just negative log the hydrogen concentration. So we get a pH of 9.26. And you always want to go back and see if that makes sense. You mixed a weak base with its conjugate acid, so it makes sense that the pH is greater than 7. Okay, if I have time, I'll make more. Thank you.